has been doing a lot of interesting work in real-time distributed systems for the last couple of years, and he'll be sharing a cool little side project he's been working on.
Yep. So can you hear me okay through this one? Good, that one use the handheld. Can you guys hear me all right? Cool. Okay, so hi, I'm Andy Brook. I'm the CTO of a company called Selerity, and I've been, as Sammy said, I've been doing distributed systems for a while in the banking and trading space for several years, and then for the last 6 years at Selerity. And I'm going to talk about something that you've probably all been told, which is don't reinvent the wheel. I remember being told that a few times, and the first reason is, well, we already have wheels. We got lots of wheels to choose from. Every once in a while, though, we come upon a problem where we need something that's a little bit different. My favorite is on the left is the Mars Pathfinder wheels. They're pretty cool. They spell out JPL and Morse code in the dust of Mars. It's a neat little side effect. So this is a story. It's a little bit about reinventing wheels, but I'm going to kind of talk you through the process by which we figured out that the wheels that we had weren't the wheels that we needed, and then kind of what we did to build something that would solve our needs a little bit better. So, spoiler, I'm kind of putting the end before at the beginning of the talk. We did, in fact, invent a new messaging protocol. I'll use new in air quotes. I'm going to talk a little bit about why this was necessary, kind of what problems were we trying to solve, what was the reasoning that went through it, what was the process that we went through. I'm going to go through some of the design and implementation details, talk about where some of the design trade-offs were, some of the things that we learned along the way. And I'm going to talk a little bit about just kind of what we do with it, how it works, how well it performs. And then kind of what's next, and then a question for the audience. So first of all, in case if you probably haven't heard of Selerity, we're small and we kind of stay under the radar, but we gather a lot of information, news, social media, government disclosures, corporate disclosures. We pull them all in. We do all kinds of different domain-specific analysis. So this is a lot of NLP and machine learning, pulling out things like entities and topics and financial data, and we deliver that in the form of data feeds that go out to people who are doing algorithmic trading. These are used in the banking and hedge fund sector. We're getting much more into the media sector today, so doing things like saying this information is relevant to this audience, or this is a news article somebody might be interested in reading. And in the course of doing doing our jobs, we have to pull information from a really large number of different sources, and those sources tend to be geographically distributed. And we have latency sensitivity that really covers a pretty broad range. Some of the financial data that we deal with really is sensitive down to a scale of tens of microseconds. There are a few things that are actually sensitive a little bit below that for things like embargo releases. And even in the new stuff that we're doing, it's still somewhat latency sensitive. You're typically in sort of the 100 millisecond range. So nothing compared to what we were doing for the first couple of years of the company's existence, but still something that we have to keep in mind. So just as a sort of in your head thinking about something that we might do, the headline comes out, Apple announces record earnings. Someone's going to want to buy Apple, and they're going to want to do that within a very small number of microseconds from the time that headline comes out. Individual investors want to hear about this story. Publishers might want to decide to put an iPhone ad next to that article because, hey, they're both about Apple. So there's a lot of natural language processing, statistical machine learning. This is all happening sort of inside of Selerity, but across a very wide geographically distributed network. So a little bit of the backstory of why we got into finding ourselves in the need for a new messaging protocol. We had the first generation architecture that we built when the company was formed in late 2008, and we sort of built this architecture out in 2009, was really aimed at the ultra-low latency financial services community. So this is all dedicated hardware, networks that we control. This is 10 gigabit fiber that we're running between our cabinets and the cabinets of our customers, co-location. And pretty much from a messaging standpoint, you're doing everything in multicast. So it's multicast with a very thin custom protocol on top to deal with message identification and parsing. So about 3 or 4 years into the generation of the sort of the life of the company, we started seeing opportunities for taking some of the things that we'd built in this ultra low latency space and applying them to more general media monitoring, advertising, things of that sort. And the challenges there were that it was much more widely distributed. It wasn't the sort of stuff that we could pack into a data center in Secaucus or Chicago or Frankfurt or something like that. We also started finding that the advent of the cloud was a clever idea in 2008 or 2009. By 2012 and 2013, it was hard to imagine a technology strategy that wasn't going to leverage the cloud in some way. And we found, as we we use Amazon Web Services fairly heavily. One of their limitations is they really don't like multicast. It's just something that doesn't work for them. So we started saying that, we're going to need a different way of moving data around. But that should be no problem, right? That's kind of a solved problem. Everyone does that. So our first step was, don't reinvent the wheel. Let's spend some time thinking about what we're looking for, and then evaluate some of the existing solutions that are out there. There's a lot of stuff that's available commercially, and there's a huge amount of stuff that's available open source for handling distributed messaging. So the first step for us was figuring out, well, what exactly do we want to do? One of the things that was important to us was high availability. We were talking to potential customers who said, look, this service is going to really, I'm going to run a very public facing website, a large news aggregator that has, north of 100 million uniques per month. This can't go down. So it has, high availability is important. As I mentioned earlier, the actual sources of the information are really spread across the globe. We're pulling stuff, our primary languages are English, Chinese, Spanish, and Portuguese. That means that we're pulling stuff from North America, from Asia, from Latin America, and a reasonable amount of Europe. So in terms of where things are physically located, there's really no option to sort of put everything in one room or on one server. Latency, as I mentioned, is still pretty important to us, although not anymore at the scale of microseconds. It's still sensitive in the scale of milliseconds. Stream processing is really important to us. A lot of the sources that we deal with tend to deliver either information that is large or is very slow to come out. We don't want to wait for the entire document to arrive before we start working on it. We also find that there are a lot of data types besides text, video and audio, that we want to be able to address in the future. So stream processing, the ability to deal with messages as streams rather than as sort of atomic documents was important to us. Language independence, I'll talk about this a little bit later, but at Selerity we're fairly heavy users of 3 or 4 different languages. So fairly heavy in C++, Java. JavaScript is coming into a lot of our applications that are user-facing, and we're getting more and more Python. Our data science team is finding that there's just an awful lot of resources available from the open source community in Python. So coming up with messaging protocols that support at least those 4 languages is important to us. Almost as important as understanding what our requirements are is understanding a little bit about what isn't a requirement. What are the things we can trade from an engineering standpoint? One of those is persistence and high reliability. The types of systems that we're building, the occasional loss of a small number of messages isn't a really big deal. These are news articles, these aren't bank transactions. What we can't have is we can't have the entire system being unavailable. So loss rates at the order of 1 out of every 1,000, that would be really bad. But if it's 1 out of 1,000,000, that's probably okay. We don't need the ability to do retries, replays, sending the information out a second time if someone didn't receive it. Most of the information that we're dealing with for this part of the platform is it happens in real time. Either you get it and do something with it or you don't. There are persistence layers that happen upstream for the originating sort of incoming source data, and we persist all of the final results of all the transactions, and that's an entirely separate process. This is really just the real-time layer. So we can really jettison a lot of the requirements for storing and replaying and transactionally processing this information. Message delivery order, except in a few very specific cases, message delivery order is simply not a big deal for us. If the messages come in different orders, that's all fine. Volume for the platform today, the big caveat is today, 6 months from now this may be different. Handling on the order of 1 billion messages a day and 100 megabit per second of peak volume is adequate for now, and that buys us enough headroom for what we're doing. Ultra low latency, like I said earlier, is also not something that is a high priority requirement for us. Tens of milliseconds is good enough. Again, we're dealing with things that have to move across very large distances. The geographic latency is almost always going to dominate most of these computations. And finally, from the standpoint of infrastructure, something that is manageable and deployable to the scale of a few hundred servers is adequate for what we're doing right now. Someday this may be a problem where we want to be able to deploy it to thousands or tens of thousands of servers. That's just not something that we're going to deal with in the next few months. So we looked at a bunch of different options, and like I said, one of the good things is there's a lot of options to choose from, and one of the bad things is there's a lot of options to choose from. We were already using a tool called Hornet Q. We use it internally for some non-latency sensitive applications, some admin, some reference data systems, and we had some pretty good operational experiences with it. So we tried that out. That worked okay. We actually ran it in production for almost a year at relatively low volumes. We ran into, in the end, we just couldn't make it scale for, even for the relatively modest volumes and timelines that we needed it. And its support outside of Java was not that great. It could be adapted to work with other languages, but it wasn't great. We really liked Kafka. Kafka looked really neat. We had heard some very good things about it and had people internally who had used it at other organizations. Kafka worked really well in a lot of ways. The challenge was that scaling Kafka ended up becoming very expensive. The I/O costs for Kafka were pretty substantial. We did evaluations of a whole bunch of other messaging protocols, NSQ, Rabbit, ZeroMQ, a few of these others. And in the end, I mean, really all of them worked. They really didn't come across anything that we just tried it out and it didn't do what it was supposed to do. The downside is that we couldn't find any of them that actually met the actual requirements that we found ourselves having. So that was kind of a bummer. But we'd been there before. So when we started the company, 5 years earlier, in the ultra low latency space, we had been in the same position and found ourselves forced to develop a protocol more or less from scratch to ride on top of UDP multicast, and that really hadn't turned out so badly. So I said, okay, well, maybe it's time to reinvent the wheel again. So this is the introduction of Trout. So Trout is a peer-to-peer multipath distributed messaging protocol. The name Trout comes from a sentence that was uttered by one of our developers fairly early on when we were just talking about, do we have a better option than this or that? We said, well, could we get what we want by just using TCP, but with multiple routes? So Trout. It inherits substantially from another in-house project that I talked about earlier called Swordfish. There's a strange convention now at Selerity that things that handle messaging have to swim. Not sure why. The first prototype went live in July of last year. We ran that in parallel with Kafka through summer and fall. And by, I think it was around October, November, we were very consistently seeing better performance from Trout than Kafka at similar price points. And we were able to scale up to meet our needs with substantially cheaper hardware with Trout. So we retired Kafka in late 2014. Our volumes have grown several fold since then, and it seems to be keeping up. So I'm going to talk a little bit about the design and then go into the implementation. One of the first things that I mentioned a moment ago, come on, besides having a slow computer. One of the things I mentioned earlier is that high availability was really important to us. One of the things that was driving the commercial success of this business was the ability for this to sit behind some very large media properties and serve up some stuff that if it didn't work, people would notice at pretty large scale and pretty quickly. So one of the tasks that we had is we said, let's go back through all the distributed systems that we've worked on, both inside of Selerity and then those of us who have worked elsewhere before. Let's kind of just walk ourselves through what are all the ways in which things have failed, and failed catastrophically, not failed like lose a few messages or be wrong in a few calculations, but where the whole system goes down for a while. And the most common one was systems that had single points of failure. A dependency on a single network, a dependency on a single server, a dependency on a single piece of configuration, something like that. That was by far the most common large failure in distributed systems that we'd worked with. The second most common was systems that had been built with a hot-cold architecture. The hot-cold architecture in principle works great. You only pay for the stuff that you're using until something breaks, and then you can fail over to this other system that's been sitting cold. The problem is that the cold system works great when it's tested occasionally. The problem is that if something changes to make the cold system not work, you don't really find out until that critical moment when you try to fail over. And most of us had at least one or two experiences of a hot-cold system where the cold system stayed cold even after the primary went down. Another very common failure model was where the volume on a particular channel, this is again particularly important over wide area networks, the volume exceeds the capacity of the channel, and a lot of messaging protocols really don't handle that very gracefully. They keep trying to send the data, queues overflow, sockets disconnect, reconnection ends up slowing down delivery even more than the process was originally. We haven't found very many that failed gracefully in a case where the amount of data you want to send simply exceeds the amount of data you can send over a particular network link. We're also we're familiar with a number of cases of feedback loops. These are most common things, multicast messaging, where you have resends, and the number you start dropping packets because some of the receivers are experiencing network congestion. They send lots of resend requests that adds to the congestion. More packets are dropped. There are feedback loops that we would like to avoid. There's a couple ways of doing that in a mesh architecture. TTLs become really important. The other thing is we avoid resends. Code bugs are a fairly common cause of problems. This isn't one that we can address really from an architectural standpoint. This one is addressed primarily just through process. It is worth noting that having a phased deployment process where we aren't upgrading this code on every node all the time, but we're going through and making sure that each individual machine as it's being upgraded is stable before we go and upgrade the rest of the plant, is important to allowing us to detect bugs while they're being deployed into production, but before the entire production system has a dependency on each of those machines. So I'll show, there's a diagram that I'll show you in a moment that might make that a little bit more clear. And the last one is boundary failures. So in most of the systems that we're working with, we sort of partition our systems up and say, well, this is production, this is our test environment, this is a development environment. One of the more common causes of failure is somebody is doing some work in the production environment, copies a configuration down to their desktop to play around with something, and all of a sudden their desktop is now hooked up to production and injecting completely incorrect data, or production slows down because it's sensitive to slow consumers, and now you've got some guy sitting on his desktop in an office somewhere. Architecting the system to put up explicit barriers between the domains that address some of the human causes of, well, if I copy this configuration, how do I make sure that this configuration, after I've copied it, if I wasn't supposed to have just copied it from production to my desktop, make sure that it doesn't work anymore. Make sure it tells you very explicitly, no, this is a production configuration. You really shouldn't be able to reach the production network on that port, et cetera. We enforce a lot of those boundaries, both in the architecture of the messaging, in particular things like configuration, but we also, that works in conjunction with the network configuration itself. So a simple example of this is, like I mentioned, making sure the production environment and a test environment work on different ports, and that the routers that sit in between simply don't pass traffic on the production port outside of the test environment. One thing that's worth noting, and this kind of comes in a lot when we start dealing with systems where we address failure through having a large degree of redundancy. We run lots and lots of things so that if one of them fails, the rest, the system as a whole is available. It starts becoming more important to us whether the failures are correlated rather than the actual absolute rate of failure. So perhaps overly simplified, if I had a system that had, say, 99% uptime, meaning it was down about 1% of the time, running 2 copies of that system, if their failures are uncorrelated, all of a sudden gets me to 99.99% uptime. Whereas the amount of work I would take to remove the majority of the causes of those, the 1% of failures, is typically a lot higher. The key there, though, is correlation. Obviously, 2 systems that fail 1% of the time, if they fail at the same time, running 2 copies doesn't help. So we put a lot of thought into the architecture to think through what are the ways in which we can make the different pieces of the system less likely to fail at the same time. Not necessarily less likely to fail in general, but less likely to fail concurrently. Okay. So digging into each of these in a little bit more detail. Geographic distribution, as I mentioned, we have a dependency on a lot of different parties in terms of who provides our networks. We're sending a lot of data over public cloud and across the public internet. We have to design, we need a messaging system that can work in conditions that are not very favorable to high volume messaging. So we need to work on the assumption that at a worst case scenario, latencies in the hundreds of milliseconds are not uncommon. If you've ever tried pulling web pages down from servers that are physically in mainland China, when you're not in mainland China, network latencies that are on the order of seconds is actually not all that unusual. Limited capacity. So it's, sounds surprising. You're coming out of a data center world where you say, well, 10 gigabit is sort of the standard, and you'd be really pushing most things onto 40 gigabit at this point. And all of a sudden, you get out on the public internet and you start finding that the amount of data you can cram through a single socket, tens to hundreds of megabits is fairly typical, and sometimes less. Obviously, as I mentioned, unreliability, very high packet loss, and it's not all that unusual for a particular link anywhere to be down at a particular point in time. So if you run two different, if you have space in a particular co-location center and you're contracting with two different network providers, the amount of time that you'll find that any one of them is up is having 2 or 3 hours of downtime per month is not all that unusual. And finally, there are some unusual, some non-trivial, and in some cases, unexpected expenses in terms of the network. Some of these issues are dealt with reasonably well by TCP, but in order to deal with this at scale, we find that we have to take a lot more control over the buffering, rate limiting, the configurations for those both at the individual socket level and then in terms of how we want to balance that load across the entire network. We also wanted the ability to explicitly define multiple paths and have a lot of control over the decision making about how those messages were routed along those paths. Okay. So today, the platform that we are addressing with Trout has relatively moderate latency requirements. Again, it's by our standards, this is, milliseconds are fine is kind of a shorthand for saying, yeah, we're really not that worried about latency. We do care about latency and volume, but we find that they're usually bounded by the network. Again, if you're sending data, between, say, the U.S. and Europe, if you're getting less than 30 to 40 milliseconds one way, you're doing pretty well. And seeing several multiples of that is not all that unusual. Once you get outside of North America and Europe, it starts to, performance drops off pretty abruptly. Once you start doing anything in Latin America, Africa, or East Asia, both volume and latency tend to be tightly constrained. But we do know that latency requirements only go one way, and we do operate a hybrid cloud, meaning we still have a large chunk of our infrastructure in physical data centers where we have access to much faster networks. So we want to make sure that the behavior of the middleware itself is driven by very small fixed size fields, need to be word aligned and in binary formats that make it easy for us to address whether we're doing the writing code in C or C++, or whether we're making some of these routing decisions in hardware. As I mentioned, stream processing is pretty important to us. A lot of the sources that we deal with have really significant delays between the start and end of a document. If you're pulling content from web servers, you'll probably be familiar with the fact that you're going to end up, if the web server has been configured without any changes to the TCP configurations, you'll have TCP slow start, which means the first couple of packets will come in fairly quickly. Then there tends to be a little bit of a pause while it waits for the window to be established, and then there's a few more, and then it starts to really ramp up. If you're dealing with content where the most important part of the content tends to be near the beginning, which is very common in news. News, you tend to have headline and first paragraph are often the only things you care about. Waiting for an entire page to download is a really bad idea. So setting up the messaging protocols in such a way that throughout the entire pipeline of the different processes that we're doing, each stage can start work as soon as some of that data is available is a critical requirement. And this is one where a lot of messaging protocols really force you to choose either between everything as a stream or everything as a document. There really aren't very many that allow you to have access to both in the same API. It's also worth noting that this opens the door later to things like audio and video processing. So one of our goals, and this really comes kind of from the history of Selerity, is that our ability to be successful to a large extent has depended on our ability to deploy both hardware and software to problems. We have an interesting mix of technical backgrounds in the company, and our plant is distributed between both stuff that runs on the cloud, stuff that runs on hosted servers, and stuff that runs on hardware that we control. So we want to be able to adapt to different topologies. We want to be able to configure the system to address those different kinds of infrastructure. And so having a very explicit and fine-grained configuration of the messaging topology and very explicit control over the routers the routing logic is important to us. As I mentioned, language independence. We need to be able to support several languages off the bat, and we know that we may be supporting other languages in the future. That means that we define the protocol in terms of bytes on the wire rather than in terms of API calls. And we define it in terms of, we require external behavior of the different peers. There are suggestions made about internal behavior, but the actual requirements of the protocol are all based on externally observable behavior. And then in terms of how we select that behavior, we do take input from people who are used to doing development in several different languages to make sure that the way that we're setting things up are not going to be particularly difficult for any one of those languages. All right. So the last part about design is cost-efficient scalability. I talked about this a little bit earlier, that disk I/O ends up being one of the most expensive single components in terms of the cost of operating a large distributed system. We learned this the hard way through Kafka. One of the most effective ways from a design standpoint to avoid that cost is to remove the requirement for having persistence and replay. Explicit configuration of the network topology does give us some interesting opportunities as well. The costs of wide area networking, particularly with some of the cloud providers, end up being very asymmetrical. Amazon, for example, charges you to take data out, but doesn't charge you to take data in. So being able to configure our network to make routing decisions that can deal with that asymmetry ends up being a fairly significant commercial asset to us. So finally, we're going to talk a little bit about the actual implementation. I'm going to talk about some of the components of Trout, the concept of nodes, transports, addressing, messages and frames, or the structure of the actual data that gets passed around. I'm going to talk very briefly about the algorithms that go into making routing decisions and the algorithms that go into message reassembly, as those are the two most interesting and complicated parts of Trout. So Trout is actually a peer-to-peer network in the sense that there is no central coordination, there's no central server. You have a lot of flexibility in terms of how you define the topology. I'm going to talk about that in a little bit more detail in a moment, but there's no single central point. The nodes, each node connects to its neighbors with transports. We support TCP today. Multicast and interprocess communication are planned. The initiation of that connection can happen from either side. Right now, we actually have found that it's easier to configure that from a single side rather than having both sides attempt to connect and then have some arbitration to decide which of those connections to retain. Then the applications that participate in that network typically run a single node in process. We've been doing some experimentation with running a shared node and then using interprocess communication between the different applications on a single server, and we're not finding that to be a significant advantage. The actual API to the application looks like a very simple local pub sub. It would be familiar to anyone who's dealt with MQ or JMS. And each node, then, this is what makes it a routing network rather than just a simple pub sub. Each of those nodes can be configured to optionally forward messages on, and this can be nodes that are running in process with one of the applications. These can also be nodes that run standalone. So key to making this work is having some way of globally uniquely identifying each of these nodes. We use an 8-byte source identifier. It has to be unique across the domain for a period of time that corresponds to how long information that we cache about each source is maintained in memory. That's typically on the time scales of minutes, which means that we need to be able to say that this identifier is unique for a period of time that's similar to that. We achieve that by assigning a statically assigned 4-byte indicator. We can use public IP address. There's no requirement that it has to match up with IP addresses, but that's a very convenient way of ensuring that we have uniqueness within the network. 2 bytes is a hash from the current time, and then there's a 2 bytes of random salt that helps us to avoid collisions. All that state information is then associated by source, and we have the ability to optionally associate descriptive names with those source identifiers. So in terms of the actual structure of the messages, they're just arbitrary length sequences of bytes. They're not required to have a known length at the time that the message is initiated. That's the streaming aspect. The format of the payload is not something that's defined in Trout. From Trout's perspective, it's just an opaque sequence of bytes. The message's identification is based on the address of the source, as well as a message identification number, which is 8 bytes. They're not required to be ordered, but there are certain cases where that helps performance. Messages that are larger than a certain size are broken into smaller chunks for transportation. those chunks are ordered within a particular message. That's the sequencing within that message. Those are assigned 4 bytes identifiers, which means assuming a 1396 byte payload, so we have a 44 bytes header. So in most networks, that means that our practical message size is around 5 terabytes. So each chunk is assigned to a frame for transport. This is the TCP transport. This is the basic unit of routing. I'm going to go through the header fields, what they're for, and how they're used. Size is put at the beginning of each frame. This makes it a little bit more efficient when you're reading information in from a socket. You can read in the first 2 bytes and then allocate memory. Decide whether or not you want to read the rest of the socket based on whether there's enough information available to constitute a full frame. So there's a few little optimizations there. There's a few flags that indicate whether it's a single or multi-part message, that indicate whether it's the last chunk of a multi-part message, things of that sort. As I mentioned before, we use TTL, very simple TTL scheme, similar to what you're familiar with from IP. The topic is a logical topic. This is something that at the application layer, the application wants to logically segregate messages. This is something that is assigned by the application. There is currently no mechanism for mapping logical topic names to these numbers. That's something that's on our to-do list. We also have a concept of a partition. Partition is, again, something that is set by the application layer. And I'm going to talk about partitions a little bit more. But the fact that it's set at the application layer allows us to do certain kinds of coordinated distributed computing that we wouldn't be able to do with a partitioning scheme that was set in some other manner. So as I mentioned, the source ID uniquely identifies the originating node of every message, and it acts as a namespace for all the other fields. The combination of that source ID with all those other fields is then globally unique. The sequence number is assigned on each frame independently of the message or chunk numbers, and that enables us to do very efficient frame loss detection. There's some open questions right now as to whether we want to change that around, because right now it allows you to do efficient frame loss detection only if you observe all partitions. So there's some discussion about whether we want to either make sequence numbers something that is local per partition, or perhaps abandon sequence numbers entirely and use the existing message numbers. And finally, we embed a timestamp in the header field. There's a couple reasons for that. One is that it does provide an additional measure of uniqueness if we've somehow screwed up and assigned the same source ID to 2 different messages. Having the timestamp makes debugging that quite a bit easier. The second thing is that when we run a system with consistent time, I don't know if George is still here, but yes. You know a little bit about some of that. If we have our time consistently, then having each of the senders assigning a timestamp fairly deep in the protocol allows us well below the application stack to actually know something about how long it took for a frame to go from one place to another, and we can use that in some of our decision making about how we route the frames and some decisions that we make around when we want to discard things when we're faced with a situation where there's more traffic than we can handle. So the algorithm for routing is actually really, really straightforward. This is one of the things that makes implementation of Trout fairly simple. Basically, as each frame arrives from each of the neighbors, you evaluate the incoming predicate. So there's a simple concept of, this node is going to allow incoming messages for a certain set of topics and for a certain set of partitions. So there's a predicate evaluation, and if it doesn't match, we discard. Now, that also is an error condition because the peer, upon establishing the connection to that neighbor, was told this node only wants messages that match the following topics and partitions. But we double check that on arrival. We compare the identification of that frame to a cache of recently seen frames. This allows us to discard the frame if we've seen it before. So again, you'll see this in the diagram in a second, but we're dealing with a mesh network. There are always more than one route to get from any one node to any other node. So the common case is you see a frame more than once and you efficiently discard. Assuming it wasn't something you'd seen before, then you add it to the cache, check the timestamp, check the TTL, and then for all of the other connections, all the ones from which it didn't arrive, forward it on if it matches their outbound predicate. So that is basically the little loop that handles all of the routing in Trout. Locally, for each frame that arrives that matches the local subscription predicates, It's each frame is then compared to a message in progress. So in the case of someone subscribing using one of the stream APIs, as soon as that frame is found to be consistent with the next frame, meaning for that message we start off saying, well, we expect the first frame of this message to be chunk 0, the next one should be chunk 1, etc. As long as it's in order, we hand that off to the stream subscribers. In the case of subscribers that are subscribing at the message level, we have to reassemble the message. When the message is complete, then we hand that off to the message subscriber. That process of doing a reassembly of the message chunks is one of the areas that there are several different competing algorithms. The simplest one is to maintain a very simple buffer, whereas each frame arrives, we simply copy its contents into the buffer. The upside there is it's easy to implement. The downside is they're doing a fair amount of memory copying even before it gets handed off to the calling application. A couple of alternatives are to cache the frames themselves within a simple linked list structure. The frames have all been pre-allocated, so there's no memory being allocated or deallocated at that point. And then allowing the caller to effectively have a stream-like interface where they're iterating through each of those frames with a simple pointer. There are a couple of different options for that. So here's one of the slides that's probably going to make some of this help it make a little bit more sense. This is a oversimplified view of how this is deployed today in production. So between two regions, I've picked two of our EC2 instances. On the left is EC2 Virginia, and on the right is EC2 Oregon. A typical configuration would be to set up instances of Trout that do not have any, they're running as just standalone processes to act as hubs. They're going to have a large number of connections, and they're typically configured in a ring. So either a dense mesh or a sparse mesh. We found that a sparse mesh like this works pretty well. Then each of the applications that run in each of these two different sites are connected just to the two nearest hubs. So in the case of deploying an application in Virginia, is connecting to the two hubs in Virginia. A typical pattern for deployment is that applications that need to have high availability get deployed in at least two and sometimes more different geographic locations. So it's common to see an example of, well, application 1 has at least one instance that runs in Virginia, at least one instance that runs in Oregon, at least one instance that runs in Sydney, et cetera. So in the case of a simple message delivery, the example I gave you before in terms of routing effectively is just doing a very simple broadcast forwarding. So a message from application 1 is being broadcast on topic 7. Application 2 is a subscriber to topic 7. Application 1 is not a subscriber, it's only a publisher to that topic. So the propagation is pretty much as you'd expect. The main thing to take away from that is each of those, there's no single link in that diagram that if it was taken away would prevent the message from flowing. More interestingly, there's no link that you could take away that would substantially reduce the amount, or would substantially increase the amount of time that it took for the message to go from the originating producer to all of the consumers. So the other thing that's fairly obvious from that diagram is that it's a relatively wasteful way of delivering messages because every message gets delivered twice. It's wasteful in the sense that we have redundancy. What it doesn't do is it doesn't grow more than linearly. Depending on the configuration of the topology, most configurations with reasonable tuning for the sizes of cache and for timeouts and things of that sort allow you to have very reasonable bounds in the number of extra copies of a message that gets made. Okay. In the simplest case I just gave you, within the scope of a given topic and scope of a given domain, every node just receives every message. This is the simple case, right? What happens when you have a single instance that can't keep up? So the volume of messaging grows. We get to the point where a single instance of an application can't cope with that much data coming through. So we need to be able to partition our data. A simple example of how to do partition, if you have n clients, we just do partition mod n equal to c, which is the index of the client. So if we say we've got 2 clients, we just the odd partitions go to the first one and the evens go to the second. With the uniform assignment of partitions, that works well in terms of distributing the load evenly, but there are certain kinds of distributed computation that won't work in that model. I'll give you one example. Let's imagine we want to coordinate computation. It's being done across several different applications where some of the downstream applications depend on receiving inputs from several of the upstream. So here's an example. Application 1 publishes a document. Application 2 extracts entities. Application 3 extracts topics. And application 4 does something that involves the combination of entities and topics. Maybe it looks for entities that are related to certain topics as well. If it's JP Morgan and it's bank regulation, well then that's particularly important. So if we set the partition IDs randomly for each message, or based on something that was just inherent to the message but wasn't specific to the semantic content of the message, then there's a high probability that if we distributed application 4, we had multiple instances of application 4 only listening to a subset of partitions, there's a high probability that any given instance would not see both the entity message and the topic message. So one solution is to have the partition IDs of these messages set in such a way that everything that originated from that first document always gets the same partition. So there's a couple of ways of doing that. One is to say, look at the partition of the incoming message, assign the partition of any downstream dependent message with the partition ID of the incoming one. A second version of that is say, well, if the compute a hash on the document and produce the partition ID based on that hash. The net result there is that you are now distributing load based on something that depends on the assignment of a partition upstream. If that is still uniform, in other words, if the assignment of partition to document was uniform, and the rate at which messages that depend on documents are consistent, are relatively uniform across all documents, then the distribution of downstream messages also stays uniform. There are, of course, lots of cases where that doesn't happen. One of the things that we've done with Trout that is easier to do if you build the messaging protocol yourself is you can put in hooks to listen to the different operational parameters of the platform, operational parameters of the messaging protocol that are specifically important to you. So we've put in lots of hooks for things like throughputs, latency, queue sizes, loss rates, things of that sort. We aggregate the data right now, and each of those nodes aggregates data that they know about locally and how they observe the rest of the network. They aggregate that locally and publish that out as a short digest on topic 0. Doing it this way makes it easier for us to integrate a Trout network with some other monitoring and administration tools. So we use Nagios and Observium to monitor system health. One of the downsides there is that we have to enable network communication between the monitoring host and all the nodes in the network. As I just mentioned earlier, these nodes are all distributed across lots of different networks. It makes the life easier for some of our DevOps guys if they don't have to open up separate firewall holes to all the different servers for each of the different monitoring applications. Instead, they basically just look at the information that gets reported back across the Trout network from each of those peers. So I doubt you can actually read that, but that's just a snippet of one of those messages, reporting lots of local statistics on just number of bytes read and written. Yeah, that's coming off of one of our test servers. That's one of our gateways. And once we have the data, we can do some interesting things in terms of visualization. So the top one is volume in one of our networks, and the bottom one is latency. And the bottom one is interesting because, I'm not sure how you can see it, but at the very bottom of the page, you can see that almost all the lines are nicely hugging the bottom where they're supposed to. And we found that we had a couple of slow consumers. And one of the things that's nice is that we can see this based on the information that's being reported back across the network rather than having to instrument each of the consumers. So we see the latency spikes in consumption from, I think it looks like 4 or 5 of the nodes out of the 50. Playing around a little bit with just visualizing some of the different topologies in the network. This one is a lot more fun when it's live, if we had better Wi-Fi here. So I want to talk just very briefly about some of the next steps for what we're doing with Trout, and then open it up for questions. So one of the first things that we're going to be working on is performance. So the first implementation was very simple Java blocking I/O. And one of the first things you say is, wait a second, you're building a messaging platform. Why would you start with Java? There are really two reasons. One is that the applications, the first applications we're running on this platform were all Java applications. These are all using open source SVM implementations. And being able to have something that would just, that could be built, compiled in with Java was a very quick way to basically prove, yeah, this works. The basic concepts work. The current code so far has kept up quite well with what is our primary bottleneck, which is the performance of wide area networks. So, we routinely on a relatively modest machine, a 4-core Amazon C4 extra large, can keep up quite well with something in the rough ballpark of 200 megabits per second of traffic. When we find that we see congestion issues within a single availability zone on Amazon as low as 100 megabits per second. It depends. It varies somewhat from day to day and from region to region. When we look at traffic between regions, we tend to see significantly lower throughput. We do have C++ and Java non-blocking I/O versions in the pipeline. There are definitely benefits for some of the nodes that have the largest number of inbound connections. The obvious place where a blocking I/O implementation is going to perform badly is when you have a large number of inbound and outbound sockets and you don't have an efficient way of selecting. We're going to be porting some of the actual applications that run on this platform to C++ in the not too distant future, pulling some stuff out of our low latency world and pulling that up into the analytics world. And one of the things I mentioned earlier is that the memory allocation, or sorry, the assembly algo, the memory usage there is often a bottleneck. So there are a lot of alternative algorithms, a lot of alternative approaches we could take there to trade off the complexity of the algorithm versus memory utilization and speed. Configuration today is manual, and to some extent that's because it's the first and obvious place to start is just give people a bunch of files they can manage under source control. It has the other advantage that by not having centralized configuration, it makes it a lot more difficult for someone to press one button and bring everything down. It takes a fair amount of effort to actually change the configuration across the plant. However, as we get larger and larger, a few dozen servers is really easy. When you get to a few hundred servers, it's a real pain in the ass, and it becomes prohibitive at some point. Security right now is delivered entirely by the network infrastructure, so limiting access to the traffic and the fact that the vast majority of the data that we're dealing with is public. At some point in the future, we need to start dealing with transport layer security. And right now, as I mentioned, I talked about this a little bit before, but we're currently have a mechanism for detecting missed frames, but that has depends on some redundancy between a couple of different indicators and makes our headers a little bit larger than they should be. So we're looking for alternatives. Compressed transport is something that has been on the wish list for a while. Not so much for performance, although it probably would improve performance a little, as that right now about 30% of our total costs are just the raw cost of moving data between different Amazon regions. Node.js is in progress. We also have some plans for Python. We're having discussions about whether there are other languages we should support outside of Java, C++, Python, and JavaScript. Automated performance tuning. Right now, all these variables are managed manually. Finding a way to automatically tune, particularly when the performance of the underlying network changes. It's one thing to go in, characterize the network, tune the parameters, and say, yeah, this works pretty well. The problem is again, when you're dealing with networks that someone else controls, you find that 2 a.m. on a Sunday, all of a sudden the network performance drops off sharply because some component failed and they've now routed around, but the new route takes a lot longer than the old route. So having a way to automatically react to that would be desired. The last thing is, right now, the routing heuristics are really simplistic. They just route everything everywhere. Again, very high redundancy, very high reliability. There are definitely cases where we know that some links are much more reliable than others. There are cases where we really would be okay with, let's just send it once over this link and then only send it over the backup link if the primary link is not available. Right now, we're not doing that. I don't see us doing that in the near term, but long term, there are a few cases where that might make sense. So getting close to wrapping up, I want to leave a little bit of time for questions. So the first is, the usual saying, don't reinvent the wheel is usually a good idea. And it's not something to be undertaken lightly, but there are times when it makes sense. I think this is one where we've been pretty happy with the outcome. I would say that it's worth putting a lot of effort into understanding what you're building and why you're doing it before you jump in. Obviously, most of the ideas you see presented here, the idea of everything from the protocol headers all the way up to how we do our routing have all been borrowed from other protocols. There's virtually nothing that you'd see here that in isolation is new. It's also useful, though, to question assumptions. There's also a lot of things that we looked at other protocols and that we looked at other messaging products and said, we know exactly why we wouldn't do it that way. Making realistic plans and having fallback options. As I mentioned earlier, we ran this in parallel for several months with Kafka, and it was only after we had a few months of seeing message drop rates, average message latency, peak message latency, and volume perform better over Trout than they do over Kafka, and Kafka is just costing us a lot more. So switching off and moving fully onto Trout. But that wasn't something we were just going to do with a completely unproven protocol. And finally, putting some effort into sharing what we've learned from this and asking for feedback. And the question for this audience, and this is kind of where I'll turn it over for Q&A, is we've had a lot of internal discussions of, is this something that has a potentially large enough use case? Other things we've developed in Selerity, we say, well, either it's too proprietary to Selerity or it's something that, we're probably the only people in the world who would find that useful. So there's really no point in open sourcing it. This is one of the first things we've worked on where we said, it is kind of a special case, but maybe it's not that much of a special case. Maybe there are other people who would find it useful, and maybe the benefits of open sourcing it would outweigh some of the costs. So I'm interested in your feedback on that and any other questions regarding the presentation.